So my name is Qiao, and I'm one of the organizers for this SIGCOMM Paper Reading Group. And today it would be already be our 15th meeting since we started last October. In the previous meetings, we have covered quite a few different aspects of networking and system research. And this week, we will focus on Dataplane architecture design. So in particular, we will focus on we will focus on the paper from last year's SIGCOMM, which is called OptimusPrime: Unleashing Dataplane Programmability through a Transformable Architecture. So I think for today, typically our meeting consists of 30 minutes presentations from one of the student volunteers, and also another 30 minutes discussions with the authors. So today we are honored to also invited Zhikang Chen, who is a graduate student at Tsinghua University, and also the first author of this paper as our guest of honor. And our student volunteer would be Xuanhao Liu, a graduate student at Xiamen University. So I think that's a very quick introduction. So without further ado, I will leave the floors for Xuanhao to make the presentation first. Okay, Xuanhao, you can start. Thank you.
Thanks for the opening. Hello everyone, my name is Xuanhao Liu, a student for System and Networking Group at Xiamen University. Today the paper I introduce is OptimusPrime: Unleash Dataplane Programmability through a Transformable Architecture, co-authored by the Tsinghua University Future World Technology and Pupil Mountain Laboratories. First, let's move on to the first section, why a hybrid pipeline and RDC architecture is needed and how it is implemented. The pipeline architecture adheres to two processing principles. First is sequential processing, where data packets flow sequentially through multiple processing stages along a strictly unidirectional path. Second is parallel execution. Although the processing of a single data packet is serial, the entire pipeline can currently process multiple data packets in different stages at the same time. Through the deep parallel processing, pipelines can handle a massive volume of data packets at line rate, thereby achieving the advantage of extremely high throughput. Let's look at the classic RMT pizza pipeline architecture. This is an unidirectional structure where packets can only flow sequentially through each logical stage from left to right, like on a one-way street, without being able to turn back. Inject packet 1 into the structure in sequence. Packet 1 proceeds through various logical stages along the pipeline for processing, while subsequently inject packet 2 follow packet 1 through the same process. They can be processed simultaneously in different logical stages to achieve parallelization. But packet 1 cannot return to previous stage. Similarly, due to this characteristic, the pipeline architecture is awkward when handling complex and stateful tasks. Its high throughput is based on the premise of simple and fixed processing logic. Once it encounters complex tasks, its rigid structure poses significant challenge. First, let's look at the challenge faced by the pipeline architecture on the long dependency chains. Suppose that when processing a packet, we need to perform two consecutive options, C equals B plus A and D equals C plus A. Everyone can clearly see that the second operation must wait for the first operation to complete. This is a typical data dependence. Dependence within the pipeline pre-parallelization. We cannot expect one processing unit to calculate C while an adjacent unit calculates D, because the value of C would not yet exist at that point. The pipeline can only split a long chain of dependent operations into different consecutive pipeline stages to complete them. If the dependency chain even exceeds the total number of all physical pipeline stages, then packet recirculation is the only option. As shown by the red arrow in the figure, after the packet completes the calculation of E, the packet will be sent back to the entrance of the pipeline to begin a new round of processing. while this recirculation sacrifices the switch effective throughput and may lead to other more complex issues, such as data conflict. We now turn to the second major challenge faced by unidirectional pipelines, non-atomic stateful operations. Let's start with the formula xb equals xb plus a. This is a classic read modify write operation. To ensure atomic state, a pipeline stage typically implements a dedicated read modify write macro pipeline internally to handle it. However, problems arise when operations become complex. Let's look at this example of a non-atomic operation. The complexity of the formula in this operation lies in the fact that it needs to first read the value of state xb, use this value to calculate the address of another state y, read the state y, and finally calculate and write the result back to xb. So the pipeline handles complex non-atomic operations by breaking them down into simpler steps. If our packet has already moved to the second or even later stage of the pipeline, recirculation again. The packet must carry the computation result D and return from the end to the entrance to complete the final write-back operation. However, recirculation is not just inefficient. It has an even more fatal flaw, data conflict. Let's look at packet 1. After a period of delay, packet 1 will be changed to packet 1 prime after recirculation. Now, suppose immediately after packet 1 completes its read, a second packet packet 2 arrives. This is precisely the core of the problem. The timing of packet 2 read operations fall exactly within the window where packet 1 has finished read, but packet 1 prime has not yet had a chance to write back. This causes a data conflict. packet 2 performs subsequent calculation based on incorrect, outdated data, leading to an erroneous final result. It is precisely this characteristic of the pipeline architecture that makes it very difficult to handle long dependency chains and non-atomic stateful operations. Secondly, we also know that recirculation itself is an undesirable and unsatisfactory solution. Therefore, this paper presents its core argument. Enhance the pipeline with RDC cores is a better solution. First, let's look at latency. The left side represents traditional pipeline recirculation. When a packet requires multiple processing passes, it must physically traverse a very large loop, which leads to a long processing time. On the right side, when a complex task requiring multiple computation is handed over to an RDC core, all calculation loops occur at high speed around the ALUs within the core. Its latency is extremely short. Next is data conflict. The left side represents the fatal problem with previous analysis. For the RDC core on the right, packet 2 is placed into a waiting queue when packet 1 prime is being processed. This mechanism inherently guarantees serial access to stage, thereby entirely preventing data conflict. Finally, let's look at the impact on overall system throughput. On the left, if a task requiring 3 processing primitives, it means the packet must recirculate 3 times. This causes the max throughput of the entire pipeline to drop to 1/3 of its original capacity. The RDC architecture can assign the 3 tasks to core 1. Meanwhile, core 2, 3, and 4 can continue to complete other tasks. This achieves throughput isolation. The basic form of hybrid architecture is as shown. It includes a high-speed pipeline and 1 or more round-to complete cores. Simple program and packets requiring only simple processing can be placed in the pipeline. Complex programs and packets requiring complex processing should be placed in RDC cores for execution. This way, the performance overhead of complex tasks does not affect the main throughput of the entire system. Hybrid architecture bridges the gap in performance and capability by combining a pipeline with multi-RDCs. However, 3 challenges persist. First, mechanical hardware juxtaposition makes it difficult to achieve optimal resource allocation and performance. Second, interconnecting the two types of resource is challenging. Third, the programming model requires programming each type of resource separately with manual function mapping, which is often inefficient and suboptimal. So, to address the issue mentioned above, this paper proposed the OptimusPrime architecture and its three designs. OptimusPrime's first design is the intermodal interconnection architecture. This is the overall view of the OptimusPrime, referred to the ring-based interconnection. The core of the entire architecture consists of multiple transformable blocks. In this example, some of these are configured as MAUs, while others are configured as CPUs. These models are connected by two sets of ring buses. Outer ring is responsible for packet scheduling between the pipeline and RDC cores, and the inner ring is responsible for data access between RDC's cores or between cores and the pipelines. Among these, the normal path serves as the primary processing channel for packets within the pipeline. For packets requiring only simple processing, they will follow the normal path highlighted in red in the figure. Packets enter from the parser and sequentially pass through modules configured as MAUs. After completing all pipeline processing, the packet is sent directly to the deparser, ready to leave the chip. While a packet at the end of pipeline is determined to require complex processing, it will be redirected to the out ring. At this point, the packet will carry a 2 CPU field. The field indicates which RDC core should process it. The packet will be sent crosswise along the outer ring to the target processor, which is in the example is CPU 1. After processing is complete, the packet will continue clockwise and eventually reaching the deparser. In a hybrid architecture, communication between different modules is also necessary. In traditional solutions, such as the well-known DRMT architecture, a crossbar is employed, which can flexible connect any processing unit and any memory cluster. So why do this traditional solution require such powerful crossbar? The execution of a network program primarily involves three types of tasks: table lookup, stateful operation, and general computation. Among these, table lookup is the most crucial driving factor. Assuming we let each RDC core use its own independent private memory, then the huge routing table or flow table must be completely duplicated in each core. This would obviously consume excess memory resource. Therefore, a solution is to place this large table into shared memory accessible by all cores. And all RDC cores can access this shared memory simultaneously with high bandwidth by a powerful crossbar. However, frequent access to a large shared lookup table remains inefficient. OptimusPrime addressed this by easily divided tasks. It assigns large-scale table lookup tasks to the pipeline, while delegating stateful operation and complex computation to the RDC cores. This division of labor allows for the use of a ring bus instead of a crossbar. For necessary table lookups, we only need to copy and place some smaller table within the RDC cores. As for stateful operation, even if a state table is relatively large, we can partition it and place different parts into multiple cores. The inner ring facilitates communication between transformable blocks. For example, for non-atomic stateful operations, as the highlighted path in the figure illustrates, a core on CPU 1 needs to cross model to write a state stored in MAU2. This is typical of low frequency, yet essential intermodal communication. It's precisely the responsibility of the inner ring. OptimusPrime's second design is to find commonalities between the pipeline and RDC models, and based on this, build a transformer block. The fundamental reason why we need a transformer model is that different applications have vastly different hardware resource requirements. Let's look at two examples. Application 1 needs a 10-stage pipeline while only utilize 2 RDC processors. On the other hand, application 2 needs a very short 2-stage pipeline but could demand as many as 10 RDC processors. This means that to satisfy both application 1 and application 2 simultaneously, engineers might need to design a chip that includes both a complete 10-stage pipeline and 10 RDC processor. As a result, regardless of which application is running, a large amount of hardware resource will always be idle, leading to significant waste. To solve this problem, OptimusPrime proposes its core concept: design a transformable block. This model can be configured by software to function as either a pipeline stage or a RDC processor. This transformable design is what we call the max of sum solution. It only requires 12 transformable models, which can be configured for different applications as either a 10-stage pipeline plus 2 RDC processors or 2-stage pipeline plus 10 RDC processors. This design greatly improves hardware utilization and cost effectiveness, achieving more flexible functionalities with fewer resources. Please look at this slide. On the left is the core processing unit in a traditional programmable pipeline. On the right is the structure diagram of a standard RISC-V CPU. We are looking for core hardware components within these two architectures that can be shared and reused. The first and most crucial commonality is that both require access to a register area. For a pipeline stage, it needs to rapidly read and write packet header field and other metadata in the register area. Similarly, for a RDC processor, its operational fundamental involve reading and writing a series of general purpose registers. The second commonality is that both require access to data memory. Pipeline stage need to drive subsequent action based on matched result. These tables are stored in data memory. RDC cores also rely on memory to store various data. The third commonality is very straightforward. Both require access to instruction memory, whether it's the actions to be executed by the pipeline or the program to be executed by the RDC cores. These instructions are placed in instruction memory. The fourth commonality is that they both require ALU functionalities. The ALU is the computational brain that performs arithmetical and logical operations. Whether a pipeline stage need to modify packet header fields or an RDC course need to perform complex mathematical calculation, the ALU is indispensable. This slide presents the final unifying architecture of the transformable block. As you can see, all the major hardware components labeled in the diagram, register area, ALUs, data memory, and instruction memory, are the common components we just discussed. The elegance of this design lies in its ability to activate different operation models through two distinct data and control paths. Please observe the red dashed path. When functioning as a pipeline stage, the match model is active. After completing a match, it generates an action ID. The system then uses the ID to directly read a pre-configured, highly efficient action instruction from the instruction memory, which is then handed over to the ALU and SLU for execution. Please observe the green slot path. When functioning as an RDC course, the decoder is active. It fetches and decodes instructions one by one from the instruction memory based on the program counter, and then dispatch them to units like the ALU and SLU for execution. Now, through the next few slides, let's take a closer look at how this one-to-many transformation is achieved through allocation pairing components and what the associated costs are. Firstly, the figure illustrates how the model operation in pipeline mode. for parallel processing unit A1 to A4 within stage A, simultaneously operate on different parts of the PHV. After processing, the results are read back to the PHV and then passed to stage B, which also contains 4 parallel units and so on. In pipeline models, A1 to A4 function is an unified whole. When this model is switched to RDC mode, these parallel hardware components are reallocated to different cores. The first parallel unit from stage A, B, C, and D are packaged together to form an independent core 1. Core 2, 3, and 4 are formed similarly. In this way, a model physically designed for pipeline parallel processing is logically transformed into 4 independent RDC cores. The cost of this transformation capacity is very low. The transformable block merely adds some amount of extra logical and wiring on top of a standard match action unit. You can refer to this results overhead comparison table. In the FPGA implementation, the relative overhead of various results is around 50% or lower. In the more critical ASIC implementation, the chip area of the transformable block increased by only 5.38% compared to a standard MAU. This minimal hardware overhead of less than 6% allows this model to transform into a powerful RDC processor containing 8 RV32I cores. This fully demonstrates the cost effectiveness and efficiency of the design. The next question is, how should we program such a novel architecture that contains 2 types of processing units? In this session, we will introduce unified programming interface we designed for this purpose, which is essentially an extension of the P4 language. Let's first look at the traditional separate programming model. Programmers need to use 2 completely independent languages and tool chains. For the pipeline portion, they use the P4 language and P4 compiler to define packet processing logic. For the RDC cores, they need to use a general purpose language like C and its corresponding compiler for programming. The biggest problem with its separate programming model is that programmers must manually partition both software and hardware. In the software partitioning process, programmers need to decide when to use P4 and C language. For hardware partitioning, programmers also need to manually determine the number of the transformable model to convert into pipeline stage and RDC cores. To solve this problem, we propose a brand new solution called unified programming. In this new model, programmers only need to write a unified program use the P4X language. This program is then submitted to P4X compiler. The compiler automatically performs intelligent partitioning, which includes analyzing and segmenting the user program to determine which logic is suitable for the pipeline and which for the RDC cores. Configuring the underlying transformable model to decide how much hardware resource to allocate it to the pipeline and how much to the RDC cores. The next key question is, how does the compiler decide which part of a program should continue to be executed in the pipeline and which part should be diverted to the run to complete course? The ultimate goal of our partitioning is to maximize the system overall throughput. For the pipeline, once a task is assigned to the pipeline, the processing speed is at the line rate, which is the highest speed the hardware can achieve. Therefore, the throughput of the pipeline portion is constant and optimal. For run to complete course, its throughput depends on 2 key factors: the number of RDC cores and the time for one packet processing. However, due to various conditions, the actual processing time for each packet may vary. Therefore, the compiler only considers the worst-case time required to process one packet for optimization, which can be ensured that the system's throughput will never fall below a reliable lower bound at any time. Now, let's look at how the compiler specifically executes this partitioning process. The first step, the front-end and the mid-end compiler receive the P4X program written by the user. Then, through a series of steps, it converts the program into a more match-friendly intermediate representation, the control flow graph. This CFG forming the basis of our subsequent partitioning and optimization. With the CFG in hand, the backend compiler began to split it into two parts, one for the pipeline and one for the RDC course. Consider the first possible partitioning method. As shown in the figure, the compiler allocates the vast majority of the logic to the pipeline, leaving only a small portion for the RDC. Under this allocation, we only need to configure a smaller number of RDC cores, and the processing time for each packet on the RDC cores will be very short, because the tasks assigned to it are very simple. For the alternative, it can also offload most of the complex logic to the RDC cores, retaining only the simplest part in the pipeline. The outcome of the approach is entirely opposite. So, as you can see, how the CFG is partitioned directly determines how many RDC cores we need and their processing load. The complex ultimate task is to weigh this different partitioning scheme and find that unique optimal splitting point. Alright, in the fourth section, we will demonstrate its advantage through a specific evaluation use case in network caching. Before we introduce our solution, let's first review the process of a stand key value querying result in network caching. The scenario involves three main roles: the client, the switch, and the server. When a client needs to query data, it sends a key that passes through the switch to the server. After querying the database, the server returns the corresponding value to the client. In the previous section, we saw the complete process of a traditional key value query and its inefficiency. Now, with in-network caching, the client still sends a key that arrives at the switch. However, the switch first looks for the corresponding value in its local cache. If found, it can return the value directly to the client. This not only reduces querying latency, but also eliminates the load on the server. The key to an efficient cache lies in its replacement algorithm. As illustrated, the LRU algorithm updates its list by moving a just hit element C to the top. If this LRU list is implemented with a linking list, the move C to the head operation requires modifying the points of its preceding node B and succeeding node D. For example, by exceeding an operation like next B equals next B. This is precisely the challenge of implementing LRU on a pipeline. Such a linking list operation, which requires read-modify-write access to multiple different memory addresses, is a typical non-atomic stateful operation. This is difficult for a traditional unidirectional pipeline to handle directly. Since true LRU is difficult to implement, how does existing programmable switch like Tofino handle it? For example, the well-known P4 LRU scheme uses hashing to dispatch different keys to multiple fixed-size, very small LRU buckets, performing LRU replacement within these small ranges. While this cleverly bypasses the difficulty, it is essentially a compromise and approximate, and its performance and cache hit ratio cannot compare to a true global LRU. Facing this challenge, our OptimusPrime architecture can leverage the unique advantage of a hybrid architecture. We designed a two-level caching solution on OptimusPrime. First level, level 1 L1 cache. We utilize the high-speed characteristic of the pipeline to implement a simple L1 cache. If a request hits in L1, it is immediately returned to the client. Second level, L2 cache. If L1 misses, the request is sent to the RDC course. Because RDC course possesses powerful communication capacity and flexibility, we can implement a complete and precise LRU algorithm on each core. If L2 hits, it is also directly returned to the client. Final solution. If L2 also misses, the request will finally be sent to the server. Through this layer design, we leverage both the high-speed lookup capacity of pipeline and the RDC core's ability to handle complex stateful operations, thereby achieving an efficient and precise LRU cache on a programmable switch. Let's now look at its performance in actual tests. This slide presents the most critical performance metric, the cache hit ratio compression, which directly reflects the effectiveness of an in-network caching system. Experimental results show that across all traffic patterns, our two-level caching solution's hit ratio significantly outperforms the P4 LRU scheme and is very close to the theoretically optimal ILRU value. As indicated by the text on the right, this means our solution successfully reduced the number of requests that need to access the backend server by 40.9% to 44.9%. Our OptimusPrime architecture can utilize resources from all transformable models, whether as pipeline stage or RDC cores, thus allowing for a larger cache and enabling a superior true LRU algorithm. This slide highlights the critical role of RDC cores in our architecture and the impact of pipeline length on system throughput and latency. First, let's look at the throughput graph on the left. As K increases, the RDC cores become a bottleneck, causing the throughput to drop sharply. This proves that for caching-intensive application, sufficient RDC cores are key to maintaining high throughput. Next, looking at the cumulative distribution function of latency on the right, we can see that as K increases from 2 to 8, the entire latency curve shifts to the right. This means that the average and maximum latency for processing a single packet both increase. This indicates that while a longer pipeline can handle more simple tasks, it may also increase the overall packet processing time. Together, these two graphs reveal a core trade-off. The resource allocation between the pipeline and RDC cores directly impact the system's throughput and latency, thus in turn, demonstrate the value of our transformable architecture. To sum up, OptimusPrime is a novel programmable network chip architecture which supports coexistence of pipeline and RDC cores with transformable hardware blocks and allow flexible block partition between pipeline stage and RDC processor based on the optimal code mapping conducted by the compiler over an application. It also continues the P4-based programmable paradigm and achieves good performance in various networking applications. That's all. Thanks for listening.
Okay, thanks Xuanhao for the great presentation. So now let's move to the discussion flow. So we have a great honor of having the first author, Zhikang, here to share his insights and experience about this work. So does anyone here have questions? We can just say it here or type it in the chat box, and then we can discuss with the author.
I have a question.
Okay.
In the future work, in the runtime of the program, the transformer block can be converted to pipeline or RDC cores, dynamic to maintain the demands the program in the runtime.
You say in the runtime, I can dynamically transform a pipeline block to a RTC block?
Yes.
Yes. In this design, it is impossible because it is dependent with the program you downloaded to the OptimusPrime architecture. So if you want to transform a block from a pipeline block to an RTC block, you must give another program another P4X program, and it will reconfigure all the architecture. You may notice I had published another paper in NSDI 22 that introduced IPSA, that is runtime configurable architecture for IMT. It is different from OptimusPrime. OptimusPrime is taking advantage of its ring-based interconnection, but it is also limited by the ring-based interconnection. Its interconnection, it is not a crossbar. A crossbar can connect the transformable blocks in any way you want, but the ring-based interconnection must follow a linear form.
Oh, okay. Thank you.
Sorry to interrupt you. So my takeaway here is that maybe the Optimus Prime need to recompile the program when the operator change the program configuration, right?
You say when the operator change the program configuration, it will pass a compilation process, and it will reconfigure all the configurators in the OptimusPrime architecture.
Yeah. So I think this is why it cannot support runtime reconfiguration, right?
Yes, it cannot support runtime reconfiguration. DIMT supports by some flex core, because DIMT has a crossbar. I think the main problem is on the crossbar with our ring-based interconnection.
Yeah, I got you.
So I think maybe the crossbar is all bars can be the future architecture for especially NICs, smart NICs, or DPUs or IPUs, like AMD Pensando DPU or Intel IPU, or Huawei's P4RTC in NSDI 25. It is all use a crossbar.
Yeah. So following this question, which is about runtime reconfiguration, it reminds me of another paper. I think it's on NSDI 2022. The title should be a runtime programmable switch. The first author is Jia Rongxing. Do you know that paper?
Is it flex core?
Yeah.
Yes, it is based on DMT.
Yeah.
Yes.
So what is the key difference here? Can we borrow some ideas from that paper here, so that we can make OptimusPrime runtime configurable?
Oh, okay. My team also published a paper in NSDI 22 that the first author is Feng, and I'm the second author. It is also about runtime reconfiguration, and it is based on the traditional IMT architecture, and we designed another a variant of IMT that is IPSA. In that architecture, we also used a crossbar to connect the the processors and the memory. And in OptimusPrime, it is just like the traditional IMT architecture. Every transformable block, either the pipeline stage or RTC processor, it has its private memory space. So it cannot just visit just access another processor's memory space. And that's the problem that OptimusPrime that it is limited that it cannot support runtime reconfiguration. And we are also trying by some of my teammates that they are trying to make OptimusPrime connected combined with the IPS8 architecture that is published in NSDI 22 to make it to support runtime configuration, and it is also we are trying to combine it with another paper I have published in NSDI 24 that that supports some complex straightforward operations in the IMT pipeline.
Cool, wonderful. We got a question from the audience in the chat box. What is the fundamental limitation for OptimusPrime?
I think it is the ring-based interconnection. It is we designed in ring-based interconnection for lower memory lower resource consumption in our FPGA or the ASIC, but it is we have found that it is a fundamental limitation. Just like the limitation of runtime reconfiguration, it also limits OptimusPrime to do some programs like I want to make a program to run it on RTC and pipeline and RTC again and pipeline again. OptimusPrime cannot support these functions.
Due to the resource limitation, right?
Yeah, yes. We want to consume less resource, but the ring-based interconnection also limits OptimusPrime's programmability.
Okay. Yeah. Following this resource limitation, I'm just wondering, can OptimusPrime be shared by multiple different applications? In the current paper, I think OptimusPrime currently focus on offload or offload single application for its performance or other purposes. So
Right.
I'm just wondering if it is possible to be shared by multiple applications.
Well, if you think P4 can be P4 pipeline, just like Interactive can be shared by multiple applications, OptimusPrime can also be shared by multiple applications.
Yeah, but here your ring design. So I think whether it is possible to incur some bandwidth bandwidth contention or isolation problems for the interconnect, right? interconnect?
Yes.
Yeah.
The computation in the inner ring. You know I have two rings in
Yeah.
my architecture. The computation in the inner ring, we have some evaluations in my paper. In our paper, and in outer ring there is no remarkable computation in our experiments.
That's cool. So based on these results, I think in the slides, I think there is a claim that for some applications they only need some very few onboard resources, but for other applications they need many onboard resources. Here the pipeline and RTC cores. So I think if we can share offload multiple applications that have different resource requirements together, the onboard resource efficiency, including the RTC core resource utilization and the pipeline resource utilization, the overall utilization will be better. So I think we maybe it is possible to build overall framework to coordinate these applications, so that we don't need to build new hardware to support these needs. Do you have
Yes.
do you
This
have
is
some ideas on it?
software problem.
Yeah.
That I think Mr. Lin Jiaxing from UT Austin has published a paper Alkali in NSDI 25 that has solved a lot of problems in this concern in the smart NIC.
Yeah.
Yes, and my teammates are also trying to advancing the P4X language in this paper to make a more perfect perfect software compiler platform.
Oh, so maybe there will be some optimization problems in the compilation stage.
Yes.
Yeah.
Maybe
Okay.
P4 is not so smart.
Yeah, I got you. Another question from the audience: what types of application and function is particularly hard to be programmed in OptimusPrime?
Hard to be programmed. In our design goal, all applications or functions that can be programmed in P4 that can be also programmed in OptimusPrime. It is just an alternative of P4. But if an application that is not that can be not programmed in P4, it is it is likely to not able to be programmed in OptimusPrime as well. It is because that I mean not running efficient. Okay. Not running efficiently. Yes, I think if you make every transformable block to be a pipeline stage in OptimusPrime, to be yes, in OptimusPrime, every transformable block is configured to be a pipeline stage. So the OptimusPrime architecture is just a P4 or IMT architecture. So any program that can be running efficiently in P4 pipeline that can be also running efficiently in OptimusPrime. But for other other applications that I cannot give a complete answer for this question because we have just tested some of the cases to in the architecture.
Yeah. So what you are saying is in the paper in that for example in network catching stateful network functions, right? So
Yeah.
so I'm also wondering in today's AI data centers, would it be possible to use OptimusPrime to offload some important network operations such as collective communication?
For collective communication, there is a problem because we have not included a shared memory in the in the current design of the OptimusPrime architecture. Although we have included the shared memory in the paper, in the picture, but we in the paper we make it a future work, and till today it is also a future work.
Yeah. So in your opinion, would it be possible to do that? And what's the potential challenge will there be?
In my opinion, we should transform the memory system or subsystem to a new one. In today's architecture, Dataplane architecture, for OptimusPrime or IMT or Bluefield 3 or AMD Pensando,
Yeah.
they have different memory subsystems.
Yeah.
And if we want to make it support just like collective communication, it will need a different controller for the memory subsystem.
Yeah. And as well, I think if OptimusPrime is used for designing smart NIC or just NIC at the end host, maybe we need the network stack, right, on top of the communication on top of the collective communication framework. So I think the possible challenge might be OptimusPrime need to support high performance network stack.
Yeah.
Yeah.
It is used in a smart NIC or DPU. It may add some other modules to the architecture.
Yeah, that's an interesting angle, I think. Yeah. So yeah. So I think from the high level, it seems to be not easy to transform the semantics of a complex C program and P4 based packet processing program. There should be many engineering work, right? So what are the key implementation challenges in OptimusPrime? I think you did a lot to yeah.
Yeah. For me, I am engineering in FPGA. So I am the hardware work. I just do the hardware work. I'm not so familiar with the compiler, but the compiler is indeed difficult work. They have over 20 20K lines of codes.
Yeah. So how do you manage the tough time or the hard engineering during this work?
I think in the beginning, Bing Liu, my tutor just gave me the idea that you can transform MAU to a CPU, but I take a lot of time to find the connection or the relationship between the two architectures. In the end, I used the traditional 5-stage pipeline of RISC-V CPUs, and that is not an efficient CPU design.
Another question from the audience. What is the most challenging part during the design? Any aha moment?
Most challenging part?
Yeah.
During the design. I think it is our problem, the ring-based interconnection. It is different from another ring-based interconnection design I published in NSDI 24. I pay a lot of attention to the possible contention in both the outer ring and the inner ring.
Yeah.
Yes, fortunately, in our experiments, the contention is not not so terrible.
Yeah, the performance contention is the first thing that comes to my mind when I see this design.
Yeah.
So
in the beginning, I think from where the in outer ring, I can make the PHV both from the pipeline to RTC or the RTC to pipeline, but it may cause a lot of contention. So I make the pipeline in front of the data path, and the RTC cores are just behind them. So it is only one way, that is from the pipeline to the RTC, that can that can make the contention not so terrible.
Yeah, that makes sense. So yeah, considering we are around the end of the time, I just have the final question. So in your mind, for a new student who is not familiar with this field, and he or she would like to take some exploration in this field, so what would be the best way to get started?
You means the designing of a Dataplane, programmable Dataplane architecture. I think the first step should be to search for some open source codes in GitHub. That a lot of papers published in NSDI or SIGCOMM has make their codes open source.
Yeah, but considering there may be some difficulty in the FPGA ecosystem. Yeah, I heard a lot of complaints in in programmable data plane, especially in terms of FPGA engineering, it is not easy to, for example, to debug or write some code and test. Yeah, so what is the best way to face this kind of challenge, in your opinion?
Well, I know that Professor Yang Xiangrui from National University of Defense Technology (NUDT) in China has published a paper of fast IMT. In yes, it is a subset of the IMT FPGA codes, and maybe it can be easy to learn for new beginners.
Okay, cool. That I also think that would be helpful. Yeah. So yeah, so today the time is almost up. It's over the 12 o'clock. So we are coming to the end of today's meeting. Let's give a big thank you to Xuanhao for the wonderful presentation, and also to Zhikang for joining us and sharing his great and wonderful experiences and insights in the programmable data plane. So it was great having you here. This paper brought up a lot of interesting points and sparked some great discussions. It definitely gave me a lot to think about, and I think all the audience will also have a lot to think about. So thank you all again for joining today's reading group. I hope you enjoy it and got something out of it. And of course, we'd love to see you again in our next SIGCOMM reading group. All right, that's it for today. Good night and have a good day. See you next time.